Let us now go to force. What is force? It is anything that can change the state of motion of an object like a push or a pull. To understand more about force, let us watch the following video.
Force. We hear the usage of this term many times in our day-to-day life. We might not know that we're using it. Opening a door, riding a bicycle, lifting an object are few of the most common things that we perform in our daily lives, and all these require a force. What is a force? Consider a ball lying on the ground at rest. It's not moving. Suppose this player here wants to pass this ball to his teammate who's standing on the other side of the pitch. How will he do that? He needs to make this ball move in the direction of his teammate. So he will kick the ball in the direction of his teammate. When he kicks the ball, we say that he applied a force on the football. Yes, the kick is nothing but the force he applied on the ball. Now suppose that we have a desk here at point A. A person wants to move this desk from point A to this point B. Again, how will he do that? Here, he will push the desk towards point B. In this case, we say that the person applied a force on the desk in order to shift it. The push here is the force that the person applied on the desk. Similarly, when you lift some object from the table, we say that you applied a force on that object. Here, the force is applied in the form of lifting. So, forces are nothing but actions such as kicking, pushing, lifting, etc. performed on objects. There are many such actions that we can perform. We have already seen few of these. Some more of them are given below. While riding a bicycle, we pedal it continuously to keep it in motion. Here, pedaling is the force that we apply on a bicycle. Hitting the hammer on a nail is also a force applied on the nail. What about stopping a moving ball? Yes, even stopping the ball means we are applying a force on it. We applied some force to stop the ball. Opening a drawer, plucking the string of a guitar, moving a piece on a chessboard are some of the other actions performed on objects. So performing these actions on objects is nothing but applying force on them. But these are just a handful of simply too many actions that we can perform on the objects. And it's not possible to write each one of those. But we can categorize all these actions into two basic ones. That is, we can describe all these actions under two actions, namely pushing and pulling. For example, when we open this drawer, we are simply pulling the knob of the drawer to open it. Similarly, when we are drawing or lifting a bucket of water from the well, we are pulling the bucket towards us. What are the actions that can be described under pushing? Actions such as passing the ball, hitting the hammer on the nail, etc. can be thought of as pushing an object. Are there any actions that can be described under both? Yes, there are. Suppose there's a book on the table, you can either pull it towards you like this or push it away from you like this. So moving an object can be described under both. Similarly, opening or shutting a door can be thought of as both. So we can safely say at this point that the forces are nothing but the push or pull applied on objects. Forces are due to interaction between the bodies or objects. What does it mean? Let's go back to our first example of this video. Here, in order to pass the ball to his teammate, the player must move it. That is, he must interact with the ball to move it in the direction of his teammate. He interacts with the ball by kicking it. The ball and the player interact with each other. In the second example, in order to move the desk from point A to point B, he must interact with the desk. In the first part, we saw that force is not just a human pushing or pulling an object. A force is a push or pull upon an object resulting from its interaction with another object. There are two things we will cover in this video: types of forces and the effects of forces. For simplicity, we can classify forces into two types: contact forces and non-contact forces. Contact forces are just what they sound like: forces that result from the interaction of two objects in contact with each other. Are there any contact forces you know of? Of course you know a few. What happens when you softly kick the ball which is lying on the ground? You applied a force on the ball and there was contact. Applied force is one of the contact forces. Next, there is a force of friction which brings the ball to a halt. As the ball is in contact with the ground, the frictional force is also a contact force. Don't you think there was some air resistance? Yes, air resistance too is a contact force. These were some of the contact forces we know of, but these are not the only ones. Can you think of any non-contact force? What happens when the ball is in the air? It will fall down, right? What pulls the ball down? Yes, it's the gravitational pull which is trying to pull the ball towards the center of the earth. This pull happens even if the object is not in physical contact with the earth. The gravitational force is an example of a non-contact force. Other examples of non-contact forces are electrical and magnetic forces. Now, I want you to think about the next question I'm going to ask you. What all can a force do? What can be its effects? Let me give an example. A force can set a stationary object in motion. That's one of the things force can do. Can you think of the other things it can do? Assume an object is moving at a uniform velocity of 2 meters per second. If it is pushed harder, its velocity will increase. So force can also change the velocity of an object. A force can also stop a moving object. Anything else you can think of? Yes, force can also change the direction of a moving object. If a ball is moving towards the north, a kick from the right can change its direction to northwest. Is there anything else you can think of force can do? Come on, I want you to think really hard. Don't think only in terms of motion. A force can also change the shape of an object. If we apply force from both sides to a spherical ball, its shape changes. The ball's position does not change, but its shape does. So these are some of the things that force can do.
Let's look at this example. Edgar fills his toy cart with stones and pulls it up the hill. What two major forces acts on the car as Edgar climbs the hill? Now, take note that what will be the answer here? The answer here would be letter, what do you think? It is letter C, gravitational and frictional forces. Of course, since you are doing it here on Earth, so the gravity is acting upon it, and there would be frictional forces because, of course, it touches the ground. So anything, if it touches the ground and you're moving it, there is friction. Let us now go to Newton's laws of motion. What is the first law of motion? It states that any object in motion will continue to move in the same direction and speed unless forces act on it. To understand more about this first law of motion, let us watch the next video.
Hi, Pedro. That's a nice smile you've got there, Pedro. Not much is happening. The ball is just hanging there in midair. Pedro blows on it and it moves because of the force of his breath. Now the ball is moving again, except this time Alexander has stopped it with his hand. And this time, nice move. Pedro changes the ball's direction by applying a force. What you've been seeing are illustrations of Newton's first law of motion. This states that every object in motion or at rest remains in that state unless an unbalanced force is applied to it. The state of motion is the speed and also the direction. The two combined, speed and direction, are what we call velocity. An object at rest has a velocity of 0 and it stays at rest unless acted on by a force. We call this tendency inertia. Here you can see Pedro applying a force to the ball. He is changing the ball's direction, therefore changing its velocity. In the second experiment, you see Alexander stopping the ball. Here he's changing the speed, therefore he's changing its velocity. The rate of change of velocity is called acceleration. Let's see what our schools have to show us. Pushing the skateboard, that's a force, isn't it? The skateboard moves, hits the pillar and changes direction. But the apple keeps going. That's because this time the force is only applied to the skateboard and not the apple. That's why eating in space isn't easy. The spoon stops, but the food keeps going. Ooh, that looks nasty. And that's why we use seatbelts. If we were in a weightless environment like the ISS, then he would continue to move. But on Earth, gravity pulls him back down. Okay, here we go again. That looks really messy. That's why we have to use lids on takeaway coffee. Thanks, girls. Good trick. Looks like she's getting her teacher in to help. That apple's not going anywhere. I mentioned objects at rest, didn't I? In these experiments, the apple, the pencil, and the girl on rollerblades are not moving. They're at rest because the forces acting on them are in balance with each other. But when the support is removed, the force of gravity, now unbalanced, pulls them to the ground. Without the force of gravity, they would just stay afloat, just like on board the ISS. So, that's Newton's first law. An object at rest stays at rest unless acted on by a force. And an object in motion will stay in motion unless acted on by a force.
Next, let's go to the second law of motion. The second law of motion is simply a formula. It is saying that the force is equal to mass times acceleration. Now, take note from this that when acceleration is 0, let me write that down. When acceleration is 0, your force would also be equal to 0, right? Let's watch the following video to understand more about the second law of motion.
I have two objects. One is red and one is yellow, and that's neither here nor there. But this one is heavier, and you're going to have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have two different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm going to do is I'm going to try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm going to put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. MacMillan Space Center, I'm Cam Cronin. Thanks again, Pernelli.
This science stuff is very serious. One ball is wooden and the other is brass. This time we have 3 balls. We're adding a ping pong ball. You can see here that things with more mass move more slowly. The second law says there's a connection between force, mass, and acceleration. So, if you apply the same force to objects of different mass, they will accelerate differently. Exotic, a stream with a steady current. There's 1 floater versus 5. I wonder who's going to win. Less mass means more speed. He's way faster. A force is applied, and according to the first law, she should accelerate. Okay, we add a heavy bag and she seems slower, plus she hasn't travelled as far. This is just like the ISS experiment. That's not a fair race, guys. Here we have magnets set up to repel each other. Magnetism is a force, isn't it? It looks like the skate carrying the load is travelling slower, and that makes sense. More mass means less velocity when the same force is applied. So, Newton's second law states that force is proportional to mass and acceleration. So the greater the mass, the slower an object will accelerate when the same force is applied. Pedro blows the balls with the same breath, but their different masses mean they move at different speeds. Newton's second law is easier to demonstrate on the ISS, but here on Earth there are other factors to complicate things. You might be thinking that the single one will land first. In the other experiments, the lighter object travelled faster, but they land at exactly the same time. We've got a crumpled page and a regular page. They've got the same mass and they're dropped from the same height, so they should land at the same time, right? But no. One of these factors is friction. Friction is the resistance between surfaces as objects move against each other. It causes objects to slow down or stop. If there was no friction, they would keep going. This complicates proofs of Newton's laws, especially because different surfaces create different types of friction. This is why we skate faster on the ice or in a smooth corridor. So, what about the papers? Was there friction acting there? Well, there was friction between the objects and the air. It was due to friction that the flat page landed after the crumpled page. The flat paper has a greater surface area and is slowed down because it experiences more air resistance. If this experiment were conducted in a vacuum, the 2 pages would land at the same time. But why did the sack of apples land at the same time as the single apple? Well, that's down to a unique feature of gravity. The sack of apples with a greater mass and the single apple with less mass are both attracted by Earth's gravity. But gravity pulls more on the sack of apples than on the single apple. But if something has a greater mass, it needs a greater force to accelerate, right? So that, in the end, both have the same acceleration and hit the ground at the same time.
We are now on the last law of motion, your third law of motion, and that is simply saying that for every action, there is an equal and opposite reaction. For example, all objects exert a gravitational force that pulls on the surrounding objects. For example, as the Earth pulls a kilogram meteor towards its center, what do you think will happen? Remember that the third law says that an object will always, for every action, there is always an opposite reaction. So what would be the answer here? The answer here would be letter C. The meteor pulls the Earth towards its center. Next example, at any given time, several forces may act upon an object. When there is an unbalanced force in one direction, what will be happening? Take note that it's saying that there would be an unbalanced force. When you say that there is an unbalanced force, that means that your force there is not equal to 0. Let us recall that in the second law of motion, this F here is actually the net force. That means that um, you are considering like as if they are all moving in one direction only. Alright, so F is equal to mass times acceleration. So therefore, if the force is not equal to 0, then that would mean that acceleration is also not equal to 0. Right? So therefore, the answer here is letter A. The object accelerates.